welcome for everyone who joined us for reinforcement learning this evening. Just a short word about organizational stuff. If you like to ask questions, feel free to do that during the session. I will take care of it. If you look in the navigation bar, you will find an icon for Q&A. This is the area where you can actually raise your questions, send it to me. We will make sure that your questions will be answered during the sessions. So also just remember that there is no silly question. Since we will really start for novice people and advanced people, you're absolutely free to ask anything which might be important for you. So again, turn to the Q&A section, not to the chat, and Q&A will be the place for questions. Anestis, I'm really happy to have you here today. Basically, we know each other for a long time, right? It's not just from yesterday. So we have been working together. So for me, it's also kind of honor to have you here. What's your relation to reinforcement learning? How did it start for you?
Well, it actually started way back in the time, maybe something like 2002, when I had my first AI lessons as as a college student. And I, like what you would expect from a young person that wants to get right into the action and still have dreams, maybe sometimes futuristic dreams about technology. I was always a technologist, and so reinforcement learning, and there is also a slide for this in my talk, really embodies this ambition of AI, where AI can actually what AI can actually become. So I was really charmed about its scope, its goal, its method. Since then, I followed it through the next years of my life on my research, on my PhD here in.
So you made a PhD about the subject?
Yes, it was my research subject was reinforcement learning. I've also worked on transfer learning a lot and several other machine learning topics, but my PhD was focused on reinforcement learning. So it was a choice of for life.
Is your background computer science, or what is your background?
Maths. My major is in mathematics, yes. But that's not to scare the audience that we will start presenting maths. We will. Some I have to warn everyone, there will be some maths, but really a very gentle introduction to this. Just what is needed to understand.
I'm sure you won't scare anyone because of maths, because I think all those people who have to do with that kind of coding or for the intelligent stuff have to do some maths. So it's just part of a game, so to say. Yes.
Yes, it is. But as any game, there are positions and roles that we have in that. And I have many friends and colleagues, business people that come from the business sector and position that still love AI. They want value from it. They want to apply that to their business. But of course, they want to avoid the technicalities. So it's very legitimate. I mean, I understand. And so I try to, and this is what I will try in my talk, to have this balance for all audiences, also for all the technologists and the AI Swiss group, to show something more advanced, say so, but keep this balance as much as I can.
That's nice of you. It's maybe also the best time to just have a little bit closer look to the audience itself. I'm going to start a poll in a minute, so don't worry. It helps us a little bit better to understand your background, what kind of job are you doing on a daily basis, and your knowledge about reinforcement learning. So this will help both of us, Anestis and me.
This is great, Stefan. I have to admit, really, that I thought of that before, and I just didn't tell you. Great that you did this, Paul.
Good, fantastic.
You can adapt accordingly.
So reinforcement learning has been part of your academic studies. Are you still working on the subject, or is it harder to do it in the daily business?
The past 3 years since we started, me and my partner, Professor Grigorios Tsoumakas, we started Medoid AI, machine learning agency here in Greece. I've stayed only on the research part of this work, mainly, and still I'm trying to find, applications or cases that we can actually apply reinforcement learning. It always depends on the client projects and what is suitable and appropriate.
Makes sense.
Still finding some chances, to teach, because I'm still teach as an adjunct lecturer here in the local university. I teach business intelligence, but still there are some introductory parts on reinforcement learning too.
Cool, nice. So I think the poll is basically answered. Let's see. Yes, we have a majority answered. Let's see what's the outcome. So yes, we have a lot of data science, 21%, product manager as well. And others, so 36%. Oh, I got not really to the point to ask you the right question, obviously, but you can put it in the chat so I know a little bit more about your background, if you can give us a hint about your role. And looking to the level of knowledge about reinforcement learning, 79% are really novice, so that's perfect, right? To help the people to get into the field, and 21% have some advanced knowledge about it. So that's awesome.
Great.
Oh, let's stop the poll completely. Thanks again for answering it. We have a lot of participants already here. Welcome everyone who has just joined. I have Anestis Varantitis here from Meduit AI. As you said, you're from Greece, right? You're basically the first one from Greece, you know that?
Yes. The first joining, we mean in a talk.
First speaker.
Yeah, the first speaker, yes.
And you're from Thessaloniki, as you said?
Thessaloniki. It would be nice if I had, this introduction with some photos from Thessaloniki, but I just thought it and say, maybe I'll share my screen later, and it will be like an invitation to all watching us today, to come visit our beautiful city.
Awesome.
Please Google it, Thessaloniki, and in images.
Cool. Anestis, during the presentation, I might ask you questions in between. As the audience is always welcome to ask questions in the Q&A section. Just, you don't need to raise your hand, just put in your questions in the Q&A, and I will have a look at it. Anestis, so reinforcement learning is our subject this evening. It's basically not only about games, right? I saw a lot of reinforcement learning in the context of games, but is this the focus of this evening?
We will also discuss the applications, and I will show you different industries or application areas that you can see reinforcement learning applied. Still, this is a very challenging subject and methodology to, to see it widely applied in production. This is still a challenge for reinforcement learning. You can see, supervised learning or unsupervised learning applications are mainly what you see in production today. But still, I will try to inspire, what kind of applications and what kind of value you can expect from reinforcement learning. So we won't focus on a specific application area. We need first to understand some fundamentals. And some of this may be interesting even for the advanced audience. Just a fresh look, maybe something will be new. Their patience will be helpful. So as we advance through the presentation.
Awesome. I think you made me already so curious to listen to you. So that take the floor and start, please.
Okay, I'll try my best for all of you.
Would be perfect.
Maybe so I can just share my screen and we can begin. Like so. Okay, good. Great. So, a gentle introduction to the fundamentals of reinforcement learning. Once again, thank you for being here. I will begin with just a first intuition on the problem, on the cases that reinforcement learning has to do. Let's start with a question. So, what is common in these pictures? We can see a baby taking its first steps. We can see this famous, these days you've seen it on YouTube and anywhere else, this Tokyo Olympics robot that shoots a basketball, even from the middle of the court and succeeding, and an automated stock trading application that's This is actually the case these days. Yes, we are in 2021, high frequency trading, algo trading. Three very different cases, three very different situations. A little baby, a human being, a robot, and an algorithm. So this could also be, interactive, but it's okay. It's just an introductory slide. So I just want to say that the common theme between these three is sequential decision setting. So in the case of a baby, we can just think anatomically the limbs and the coordination with the nervous system of a baby that tries to coordinate its legs, its hands in order to walk. And this choreography, this coordination is so sensitive, just a little movement off and the baby will fall. And still the baby throughout the months will learn to walk and will be able to to solve this, what we call, allow me, credit assignment problem, to understand which little part of the sequence of its movements was the wrong one, although the end result is definite and specific. Unfortunately, our little baby fall down, but still our brain is capable to understand what little part, what single part, all the other parts of our movement were correct. There was only one thing wrong, and we can find that. The same thing with the Tokyo Olympics robot. Very, very precise movement, a sequence of movements that even just one off will get the ball out. And this sequence of movements and a history of transactions on stock trading, that everything is dependent to the next one. And the state, our current state in time, is dependent on what we did in the previous time step. This so sensitive sequence is also a characteristic of what I have there in stock trading. So the common theme, sequence decision, sequential decision problems. We will see later on in the presentation why this can't be solved with regular machine learning, what we know as this kind of problems, sequential decision problems, why these have their own distinct category. We will try to build some terminology, just a little bit, and get some fundamentals. Expressing the problem. So we have some sequential decision problem. Stefan previously mentioned games. Yes, a bot, a player bot from the game side, that we play against. It's also a case of a sequential decision problem, and adverse that fights us. So this is also a sequential decision problem. In reinforcement learning, the theory context, the theoretical, the mathematical context that we are usually referring to are Markov decision processes. We can just keep that as a keyword for our own research. So we need to build a controller, if that be a brain, another baby's brain, maybe a robot brain, if that be an algorithm that trades stocks, it's still a controller that takes decisions. We can call this actor an agent. We need to interact with an environment. We have to keep this terminology, this is very important notion, the environment, which is either the place that a robot walks or the signals we get every microsecond in a stock trading setting. And we will talk also about other applications. And what we usually know, and this is very, very, very charming in the reinforcement learning setting, is that we don't assume great amounts of knowledge. So this is a very realistic setting that can be that we can see it around us in many different cases. So in this case, we need to know what we call the state, where we are, maybe the vision of a robot, its cameras. Okay, and this is important and distinct in reinforcement learning. There is always some evaluation of our interactions. Do we achieve to shoot the ball? Do we achieve to stand upright? Do we achieve to gain some profits? There must be some, what we call As return, it's a long-term accumulation of rewards that are provided possibly from the environment. Now, a simple schema. Yes, yes, please.
To go back to the previous slide.
Yes.
You said Markov decision process. What is so specific about the Markov decision process? Is it because you said that there's a dependency of states, or what
Yes.
makes Markov decision process?
Okay, okay. So the intuition between this, mathematical framework that is chosen for reinforcement learning is that in Markov decision process, we assume that all we need to know to take an optimal decision right now is our current state. The information we have in our hands right now is all we need. We don't need any information from the past. Everything is summarized and compassed and included in our current information, all needed to take this perfect decision right now. So this is just what we call the Markov assumption. We can violate this, of course, and this makes the problem more realistic, but this also, we have also challenges methodological on that. So this is just in a phrase, Markov decision processes, the Markov assumption, that we assume there are some information right now, all the information we need to take decisions. The usual setting, and this is related to this question, is an agent, as we said, what I call the controller. You can see probably my mouse pointer, Stefan.
Yes.
Thank you. An environment, we can see this as black boxes right now in a blurry way. We always return an action. This is the choreography of reinforcement learning. We send an action to this environment, and the environment informs us about the new state we are. Where are we in this room if we are a robot? After we walk 2 meters. And a reward for this specific action that we took in this state. Now, in general, reinforcement learning is categorized in machine learning as semi-supervised machine learning. The distinct parts, some of this I talked also again, and I'll try to go quick on this, is that we assume there will be some feedback from the environment. We can't learn something without some feedback. But in the case of reinforcement learning, this feedback is not like in supervised learning, the correct action. That's a very important distinction. Reinforcement learning can learn reinforcement learning methods just by an abstract evaluation, a numerical evaluation of our actions. We don't assume there will be some teacher that will provide us with correct action examples, like in supervised learning. In supervised learning, we are learning models to discern cats and dogs in pictures. So we need to provide some examples, some photos of cats and some photos of dogs to classify them correctly. In reinforcement learning, we may have a relative evaluation of our action, if our action was good or not. And this is very realistic because usually humans and many challenging problems don't know what would be the correct choice for the agent. They just know if the result is good or not, but not what exactly that should be. So reward, and this is related to what Stefan asked me why I really love since I was a kid, reinforcement learning. So reinforcement learning is one of the most ambitious machine learning fields because it's what I call towards artificial general intelligence. There are not many approaches that really try to be the backbone of AI. Maybe we can think for that for a second, the backbone of a complete AI system. Because if you think of it, all the other major categories in machine learning and AI in general can work like peripherals, like you see here, computer vision. This is information for our reinforcement learning agent, for our robot, if you think of just a robot here in the center, in a simplistic way. Supervised learning, we can forecast things, but this forecasting is not decision on its own. It's not action on its own. If you have a forecast, that doesn't imply what you should be doing tomorrow. You know what would be good or bad tomorrow if you forecast, but this is still not a decision. So the backbone should have some decision element, and this decision element is nicely represented in many problems as reinforcement learning. Text mining, NLP, all the other cases, applications, just to inspire all the, and to show you all these uses. Of course, we all know that, and we may have heard that reinforcement learning is widely applied in games. We've seen all the successes of DeepMind and AlphaGo, all these games, mastering games that, 15 or 20 years ago would be thought impossible. Go, a much more challenging and complex game than chess. And we had these successes mainly from reinforcement learning algorithms. Robotics and automation, we can see production deploys of robots that actually use today reinforcement learning. Bidding and advertising, because if we think just for a second, for example, the click-through rate of an advertisement or the CV, this is the perfect reward signal. If these systems really learn through reward and punishment, because that's what inspired me, clicking an ad or not clicking an ad, this is a very clear signal. Personalized recommendations, we all have heard about autonomous vehicles and driving. This is not actually a production case of reinforcement learning. This is a challenging part, and it's not a mature application of reinforcement learning. What we usually see in Tesla and other autonomous vehicles in their pre-release versions is a mix of other control methods too, for greater safety and less experimentation. Now, we will try to go as fast as we can in trying to build something all together. We will try to think of a problem altogether and build constructively our knowledge. So we need a very simple environment. It's not thrilling, it's not interesting, it's a very simple environment, but this is the way that we can learn some fundamental things. And it's a toy, it's a game. So there is a little grid world. There is a little robot, a very cute one. This little robot lives in this environment. It's nice, it's okay, it's happy day in, day out. It's not, we should not feel sorry about this little robot, but this environment has some difficulties. This little robot should travel through this little grid and go to this happy place. This happy place has a reward of +1. We need to find a way to go there whenever we can. There is a little trap here, a -1. We should avoid this. And, just wandering around is not very good because there is a little punishment that we're just spending our time, a -0.04. We can think of much more complex and realistic problems that we could find such rewards. So it's not just a grid world. We can right now think of problems just before, as I mentioned, the ad placement in Google AdSense or something like that, that there would be so discrete reward buckets. So this little robot knows nothing. It just knows where it is in this grid. It doesn't know what is the reward of anything or where there is some reward. It needs to experiment and see what happens and learn, gradually learn a path to travel. What makes this problem more interesting is that if you see up here, there are some transition probabilities. So that means that the actions that the robot decides won't always happen deterministically. So there is a case, at 20%, that the robot may go wrong in any direction. So we can't just pass through next to this trap because sometime we may fall in the trap in -1. You see, there is a 20% percentage for this to go wrong. Now, this is a sequence down here of actions. We are in the box with coordinates 1, comma 1. We go north, then we take this reward. You can see the sequence that we talked just before. Our little robot should learn a way. If we place this robot here, it should go like this, go around. Let's see if we have that here. It should go around here and go to the +1 case. But this is not the fastest way to go there. The fastest way is to go through here, but this is risky. So this is a simple intelligence trait, a very simple one, but very indicative of what are we talking about, intelligence, that doing things that look suboptimal, but in the long run are actually optimal, that you can do something that doesn't look like, a greedy choice, a myopic choice of going, directly to the best thing, but having a strategy. So our little robot strategy would be to go all around, avoid the case of this trap, and go to the good case. So let's try to solve this problem right now together without knowing reinforcement learning. And we will try to solve this using supervised learning. So supervised learning, we can think everything from the extent of linear regression to any deep learning setting in neural nets. So we have examples of correct output given an input. We provide these examples and we expect to generalize outside of this example set. So we made these coordinates, we made this a data set. This is a data set, 1.1 north, and the reward is this. 1.1 north, the reward is that. In 3.3, if we go east, the reward is that. And this is our supervised learning setting. Let's pass through an algorithm and let's see what will happen. There will be many problems. What we learned here was not a policy. It was not what the little robot should do. It was just the reward function. Where there is reward, where there is no reward. This is not a guidance. This is not a decision policy. We learned something quite, allow me to say, silly, that the bigger the coordinates, the better. Look at this, 3.3 plus 1. 1.1 minus, so we learned that if we are on the top here, it's better. Okay, -1 is also has high coordinates. You can't make sequential decisions based only on local awareness. This was a local awareness dataset. We can understand that this model could be nice, but the training targets are incorrect. These little numbers, this is not what we should learn. Let's try to solve this with another method. We don't know reinforcement learning yet. We don't know nothing. We know basic maths maybe, or advanced from the college. We may know dynamic programming or planning algorithms. This is still considered part of AI literature, especially in the old days, because it's a very well-respected field. AI is not only machine learning. We should not be forgetting these days. It's a whole planning field with a lot of work there. And so we know that there is a very basic algorithm there, the value integration algorithm. We won't go in the maths right now. We will be quick. If you run this, it will get you an optimal policy where the robot should go at every step. We can do this right now, and it's not computationally efficient usually because it has to run all the sweeps through every state, and there is a lot of complexity, but it will get you, there are guarantees that it may get you the optimal policy, the best way that the robot will see the place. The problem is that this requires us to know the probability, the transition probabilities. So if we do this, where we go next? We don't know this. We assume something very ambitious. We assume that we don't know where we are going next if we do something. We know nothing. Yet, we will learn while acting and interacting. And of course, we don't know the reward function. These are required in this more mathematic closed equations setting that we are doing here. Let's try to get into reinforcement learning slightly, gradually. First, it's like a disclaimer for all of you that know that this is a huge topic. There are lots of algorithms. That shouldn't scare us because this is also driven by the application that we are interested. So each one of you, our fellows here that joined today, have some application in their mind. This application, if we search through and look, will drive you to some specific methodology, that is more suitable. And I will tell you more about this because, Stefan, there will be notes after the talk. I will share you a link with notes and some guiding material on how you start implementing reinforcement learning. I'll show you this along with a QR code that you can keep it like that. We will focus today.
Yes. Presentation will be available afterwards as well, right?
Yes.
That's awesome.
Yes, and the notes are links in interesting locations that you can all visit.
Thank you.
So we will go to the Q-learning family today, which is easier, of course, to grasp, very fundamental. You can do real things with these algorithms, and it's quite good as a first step. But for all of you that some Q-learning they have deep reinforcement learning aspects too, which are more, the wow factor that we have seen, the Atari games, AlphaGo, and all that belong in this family, but also some other great methods that belong in this category. And this is just love.
Can I just quickly ask you one question?
Yes, of course.
It's from looking at the hierarchy, the structure of what you show us here. There's a model-free RL and a model-based RL. So what's the difference between both directions?
Yes. In the model-based reinforcement learning, all what we were talking up to now is on the model-free setting that we assume no knowledge of the environment. In the model-based reinforcement learning setting, we try intentionally to learn the environment, learn the transition probabilities, learn the reward. While we're acting, we still don't assume that we have this a priori on beginning, but we have this goal to learn the environment, not learn to act, learn the dynamics of the environment explicitly, because this helps very much in cases that interacting with the environment is very costly. Because, and this is important, thanks for the question, Stefan. I need just to give a line about this. If we have this robot, a very expensive robot, I've been working in 2012 in Plymouth in the on the ICAB robot in a research lab there. A very expensive robot, okay, hundreds of thousands of euros, and you can't really run reinforcement learning on a real setting and break a limb or something in that setting. So, and in many similar settings. So in this case, it's better to know a model of the environment so that your interactions are more safe and learn faster. But there are also some disadvantages in this category of algorithms. In games, there is no cost in interacting. You have all the time in your life to do simulations, and you may go faster with the other category. So, reinforcement learning, this is a little bit heavy slide. It's not about the equation, please. I'm really trying to make this, it's just the bold letters that are important. Utility is wise. We need to learn some form of utility of our actions, not just the reward, as we said before. We need to know the utility, the long-term value of something. So we need to sample, interact and sample, and we need to learn some quantity like this. The notation is simple, trust me, it's the value, it could be V, we call it Q, and depends on the situation, of a state and an action. So in its state, whatever state we are, and whatever action we're considering, we need to know its value. What this value would be, the rewards, these are the rewards that we get through time if we do this action until we reach a goal state. Now, I will explain all these other factors later on. But important.
Because so utility is a function of rewards. Is that correct?
And not the reward on its own. Okay, single reward. It's the expected rewards from now and towards a goal case. But we need some way to calculate this because it's not very obvious. You know, we are not standing in a single place and space and accumulating rewards. We must find a way to store this value, to count these values. So in reinforcement learning, we need to learn some incremental rules. We call these updates, and these will accumulate our knowledge of values. We need to find smart ways to accumulate this knowledge and not just store it in a huge table it will get millions of rows and columns, and we need to find a smart way to accumulate and credit and gradually estimate, propagate the correct values. So in a second, we will be in a nice exercise that we will do together. This is an algorithm. We call this SARSA, a very smart algorithm. Trust me, it's 10 lines of code, and you can build very complex behaviors. You can build behaviors of this because think that it's a very simple loop, but it happens multiple times, and this builds complexity. Smart parts in multiplicity that create and emerge complexities. And this simple algorithm, SARSA, which is considered fundamental like to learning, has its heart. Its heart is this equation, this loop, this update. This is an update equation. And if you look at it, there is no intuition there. I mean, we can just look at it. It's an update, an equation. Okay, we know from maths, and there is a stress here, Q stressed, so the new value. And probably this is the old value. And this again, maybe it's the new state that we arrived or the action. It's difficult. And we don't understand the intuition behind this. So we will try to build this on our own. Forget it. We can forget this equation for a second. Let's see if we can go to this on our own. We are in a little robot world. We need to learn something like this. Look, these are not the rewards. These are different numbers. We need to learn the utility of its little square. And this will imply what we call a policy. Important keyword, please keep this in reinforcement learning. Policy. The policy are these simple arrows. Wherever we let our little robot, if we let our little robot here, the little robot should go in here. Then it should go here. Then it will reach the correct state. If we leave our little robot here, it should go around. Reinforcement learning is about learning these arrows. This is all. We need these methods exactly to be able to create a plan, to learn a plan of actions, sequential actions. And yes, please.
One more question from Synap,
yes.
Because maybe it's just now a good time to ask. It looks like he's saying, it looks like reinforcement learning is based on the classic dynamic programming. Is that correct?
Expands. Did I hear correctly? Expands. Did I? Sorry. Sorry, Stefan. You said expands.
Oh, is based on the classic dynamic programming.
Yes, this category of families, that the Q-learning part, this category of families is inspired, especially in mathematical level, from dynamic programming. And you can see this in this update rule. This update rule is very, very relevant. And it's from the Bellman equations derived and all those for those that are relevant. to this. And yes, they are very related. It's a good start for reinforcement learning. Wherever, if you want to start in more classic literature, more traditional, build good foundations, especially if you do research in RL, not just apply it. If you just apply RL, and even in interesting ways, you don't need to study dynamic programming. If you want to do research, well, it's always a fundamental part. So these values will be stored in a tabular data structure. We can imagine a table having these values. We just don't have a way to get this. How will we compute these values? And if we compute these values, we can make these arrows. Look, 0.655. This is a better value than this, 0.611. So you get on your own the arrows. You can calculate the arrows in a monotonous, in a specific way, just by having these numbers. So let's try to build the update rule on our own. It won't take us long. It will just give me 4 or 5 minutes on this, and we will see that we can get this intuition on ourselves. Let's assume that our little robot got a reward. It's happy, a nice reward. It's now in a new state, a new place on the world, on the grid world, and has just executed an action that go east, go west, whatever. Now we are ready to learn something. This is what we're doing here. This is machine learning. We need to learn if this was good or bad, and don't repeat it or repeat it again. So we can store a little value, what happened, as a memory. And we can say that the new value, this stress here on the Q, is the new value, the updated value of this state and this action, the previous state and the previous action, should be the reward. No, as we just said before, just learning the reward won't help us to take decisions. It's actually a very naive approach. It's like using just supervised learning of that. So we need to fix this. And an idea is to add the value of our current state and action that we have already decided to do. So let's see this correction. Add the value of the new place that we will go. This is quite smart. We have that stored too. It still may be 0. We may have not passed there again yet. It's a new place in our world, but gradually, while we're interacting, there will be some value there. So this is smart because you say, let's take the reward, and what reward is there after I leave? So it's like it accumulates all the future history in there. So this is smarter. It's not myopic. It looks in a more strategical and long-term way. It's telescopic because in a smart way, it uses all the accumulation of. So this accounts for future values, but there is a problem that the future values are as important as the reward. Look, it's one time the R, one time the future. Is this the case? Is today's reward so important as all the future rewards that there are there for us? So we need to add one little parameter. We call this gamma. It takes values from 0 to 1. Very nice. I think it's not annoying. It helps us to put a weight on the future. It's also has some philosophical value to it, that how much you discount future returns. So in some things we say, I need something right now, or I will put some effort because a goal is more important and there is more reward there. Now we have something. We can learn the values, but there is a big problem that every new lesson will diminish what we already know, because please think that this goes thousands of times iteratively. You go through the grid world, you pass through every new state and action, and you run this update again and again for different states and actions. So every time you do this, this value will erase the previous value. There was a value here, maybe 5, 6, a number, and now we erased it, we overwrited it. So why not add, look at this, the old value of this state and action, and just put a new factor on how important is a new lesson towards what we knew, compared to what we already knew about the state. Look at this, it's alpha times something plus 1 minus alpha, because it's the opposite. Alpha takes values from 0 to 1, the other value. If you think of this, most of you and professionals that have worked on neural nets know learning rate. This is the learning rate, how fast our learners should learn. And we should not be greedy about this, because we can really make great variance and not converge our algorithms, never. You need to set this learning rate to something that, there are many considerations, avoiding local maxima and all that, and escaping such situations. But this is the learning rate. Now, if we just multiply all this, that we came logically to that, this was the update rule. If we go back, allow me, this strange thing that we were seeing here was just a different reorder of the terms that we derived on our own here. This one thing is equal to that. And we came to this, I hope I wasn't cheating, you'll tell me, with no irrational leaps, that step by step. So other big considerations in reinforcement learning. We are gradually concluding. We need to see 3, 4 important parts of, and Stefan, thank you, please, you guide me through time whenever. There is a big subject in reinforcement learning, a big limitation, especially in this category, the Q-learning family of methods. We need to always check exploration and exploitation. This is again once more a philosophical dilemma of so our little agent. Do you want to see a video? Maybe we can see an agent exploring, a simple one, just for a second. And you will get what I'm talking about in just a second. So I will share, stop share and share again. And I will share this. This is a nice site I will have in my notes, so you can visit it. And you can see a little agent like before in a grid world. He knows nothing. You can see the 0 values here. He knows nothing. These are the values that he will learn. It's a little game. We can play it right now. It has basic reinforcement learning before, but we have this nice example, has deeper learning also too in more complex environments. It's a very nice page that you can come in and play reinforcement learning on your own and understand many notions. So we can rename the agent, toggle TD learning, and let's see our little robot trying to find its way through this maze. Let me stop it for a second to show you. Okay. No. Go slow, go slow. Look, there is a reward of 1 somewhere here. Okay. Our little robot should learn to navigate this path. There are some traps. Please note this little R-1 here. These are the rewards. And up here are and now you can see it's fixated. It has this fixation now, and now it knows where it goes, nothing changes. We can shake things a little bit by changing the reward. Let's put here let's put in this reward a bad trap. Let's take this to -2, 3. Our little robot starts to have problems now. But it can't explore. We have set it in a way that it can't really take the courage, to do something random. And this is important in reinforcement. You need to have some little algorithm, and quite simple sometimes, that will let you take another path if things go wrong. If we take this exploration up to here, we will help it escape. Let's take it far away. Okay, because it now found a way out. It's like driving learning. Okay, now it found enough, because we let it for a little bit to explore, it found another way. You see, it's gradually learning, it's continually learning. You see how reinforcement learning is different. We can play with it and change the environment while it is learning, and still it will adapt. That's why we call it usually adaptive learning. Now our little robot adapted. Nothing in our code changed. It was 10 lines of Sarsa code. Everything is fixed. We didn't give any explicit knowledge. Let's leave this example. We can go back later if you liked it, and go back to our presentation with having derived hope in. Okay, I guessed my own self. I had this demo here in my next slide. The exploration aspect is important. There are algorithms that do this. So the most simple of them take a random action after some steps. Can you still hear me? Well, Stefan, I had some thanks. Now, let's go to a more advanced topic. It's important, and I think we will be okay in maybe after this, I won't go to the much details. I will finish with some concluding slide on this. Important topic, functional approximation. This is where deep learning part that excites many of you, I know, comes in many cases, the deep learning part. And what was just before supervised learning. In my days of my research, still before 2013, there was no deep learning application on this. We were just using shallow neural nets to approximate these functions. The thing is that we have this value function, and I told you before that we need to store this on a table, these values, and we need to update each little cell with the update rule, that little telescopic function. Okay. The problem is that we can generalize, possibly, any real environment, even Atari game environments. We can store this in a tabular form. We can't learn a value for this and expect to learn a value from this, which are neighbor states, and they should generalize. Imagine this table being expanded here. We should travel through all this grid to be able to learn. Knowing this value can help us approximate the neighboring ones without having to visit. Without what we call function approximation, which is the terminology we use for supervised learning. In RL, the supervised learning part, we call it function approximation. It's the way we store our learnings while we interact with the world. We need to find a way to store our learnings that will generalize above and beyond what we know. So function approximation uses supervised learning to approximate the state action values. The semi-supervised problem is transformed to a supervised one. Very fresh insight. In a very selfish way, I take the credit for this, because this is an insight that actually a reinforcement learning algorithm transforms a semi-supervised problem that we didn't know the examples, the correct output, to a supervised one through function approximation. So the Q-learning algorithm or the SASA that we saw just before that builds these little values, it actually builds the targets of a supervised learning problem. So we're actually transforming a semi-supervised problem to a supervised one, but with the correct targets that could only be given by an RL algorithm that knows how to build these targets. The combination of RL with deep learning, of course, gave all these successes, but as with all deep learning, still, this is okay, awesome, but very challenging to have production and have some real cases and successes out there. This is why for most people that enter reinforcement learning, I suggest start with Q-learning, start with SARSA, because very simple little tools and apps that you can build and have something, an RL component running behind, even in this simple setting, will give an intelligent behavior, will give something. So you can start gradually by having a SARS algorithm, 10 lines of code, and seeing the behaviors that emerge. And then you go on more advanced cases. Okay, we can skip these. Other directions, of course,
And
as we said, yes.
Just one. I'm just thinking. So you made me thinking a lot. If you could just go back to the slide with bigger matrix. I think one step. Yes, thank you. I was just thinking of some parts of what you've said. So yes, a typical natural problem would be that we have a huge
space
matrix of what we go next, right? This is reality. So it's not this 4 to 3 matrix, and on the right side it would be the large one, as we can see here. At one point you said it's now interesting, but if you are in a cell as an agent, to predict the value of the next cell before entering it. So this is function approximation. Did I get that right?
Yes. Look, as long as we are talking, thanks, Stefan, yours to help me clear this out, because as long as we are talking about cells in a matrix-oriented table, we are not in function approximation.
Oh, okay.
We still have a tabular data structure that we store things.
Yeah.
We can now think of a neural net with weights and all that. So any place that we are has some coordinates, which are the inputs and the input layer of our neural net encoded there. And yes, as you said, we learn something, similar inputs give similar outputs. What we would, this is the principle in this. So we are in a very close in the space, spatially understanding. We are in a close situation, somewhere close to that. So the value is probably, it's an assumption, and sometimes it doesn't work. It depends on the scenario if it works. And this is generalization. That for similar coordinates, give me a similar value. Now, okay, I kept this for later on. So other directions, inverse reinforcement learning, please know this is a thrilling part. I wish I personally had time to study this. I'm always next to it, trying to read something, leaving it. I wish I will have this time. Inverse reinforcement learning is the opposite problem. We know a policy, we know a set of actions that was done in the past, and we try to think what kind of reward would motivate these actions. We try to understand what reward signal is hidden behind the sequence of actions. In the transfer learning, I've been working a lot on that. I can show you a video of a little robot I have trained in simulation in the past, just in a second, that shows transfer learning. Just right now, I will show you this. You will see now, this robot is the one I was training back in 2012. We were training it on simulation. And
I can see slide 43. Are you showing a different slide?
No, I was just not yet sharing the correct
Okay.
I will in a second. And this little, okay, now you see that, and now we can see the target task. Okay. This little robot, you will be, oh, okay, no, you lost it probably, one moment.
Oh, that was cool.
You see, okay.
Yeah, you enlarged it. That was cool.
Yes, I'm not a YouTube expert, unfortunately, and I don't know how to.
Try on the right icon.
Ah, great. Now I did it. Okay. This is the ICAB robot. If we go and check this little robot, ICAB, it's nice to know that it's a little child robot. It's tall, like 155 tall. There is great amounts of work on cognitive robotics on ICAB based on the assumption of embodiment. You know how strong principle, there is a whole school of thought on the embodiment on the importance of embodiment, on developing cognition, a future dream of. So ICAB is a whole school of thought. We are training it here. You can see it with the mask off to hit a little ball on a desk. I will take you now to the example. Okay. Okay, give me just a minute and we will be there. This is combination of transfer learning and reinforcement learning. So I am sorry for the resolution. You can see that our little robot can see, we assume that there is no vision, and tries to find happiness by moving just its waist. The only limb it can move is the waist, and has the hand like that. And it will get some reward when it hits the ball. So after many episodes, an episode is the new ball coming on the table. A second. Now a new episode starts. A new table with the ball will come. Yes. And our little robot has learned to hit the ball with this movement. Now we move on in a different situation. Our little robot can move not its waist, but its hand. So it needs to find a way to transfer its knowledge from different limbs, that what it was able to do with its waist, it should now be able to do it with its hand. It was a succeeded experiment. You can see in the first steps that it just searches the environment for something. And after some, it learns to hit the, okay, next episode. It now learns, let's get the table. Okay, great. And now it learns to hit the ball. Ah, missed it for a little. Okay. Ah, it hit it like this. So after, I'll stop sharing. After lots of episodes, and this is very funny, I need to tell you, at least for me, it learned to hit the ball with the toes of it. So it wanted to do it so fast, so quickly that not even, you know, just touch it and hit it and get the reward. Something before we conclude that we need to make very clear is the importance of the reward signal and engineering this reward signal. So this and other curses are the reason that I get this funny meme. Many people, you know, say this is very pessimistic. Reinforcement learning works, but there are many cases that may look like appropriate to try, and production cases. Still, things are not as mature as they are in supervised learning, or because experimentation is far more difficult. Experimentation needs, in many cases, simulation, needs lots of data. The new novel methods that we have seen are very data hungry, all the deep learning methods, and there is a need for great advancement on all of these cases. I can tell you more in just after I conclude on the limitations. Okay. Frameworks and libraries, I have this updated on my notes. I will send it to you just afterwards. And allow me to conclude with some life lessons learned from reinforcement learning, from what we said, the basic stuff about RL. So these are just my thoughts. They may be wrong, but it's very inspiring because RL has this philosophy of, so we can act suboptimally, but this may be a greater part of an optimal plan. We should learn at each step, not the reward, but the value. This works in real life too, that we should be learning the value of things and not the immediate reward. The reward system that we talk about, maybe in real life, it's us. We are a collective reward system for each one of us. So it's like trying to have a systemic approach on life, on how this can, and there are some fine similarities. The rewards and the punishments are above all information. Our little robot wasn't sorry. It just took this reward or the negative reward and the punishment and tried to make something out of it. We should not discount future rewards if our goal is episodic. This is reinforcement learning literature, that this gamma factor that you saw, if a goal has episodes, a little table coming again and again, episodes. So if we are to obtain a degree, we should not discount, but on future rewards for a continuous goal like happiness, we should discount future, that we should seek happiness, immediately. And finally, I'm closing with this, function approximation. If we push the resolution, if we make a deeper network, a deeper neural net, and try to approximate and generalize greater, we need more experience. We need more rows. We need to balance exploration and exploitation. I say also this from a business perspective, because you saw how the agent was stuck if he didn't have exploration, and our businesses should, for every X investment units, they should try something radical and put that in their budget plan and have this exploration policy too. Thank you very much all. I'm available, I will be, for questions. I tried, to go through everything somehow. You can take this QR code or the link. The notes will be updated on Monday. Now I have some older stuff. But still are useful. I have the basic literature links and all that stuff, but I will update them more.
That sounds pretty cool. Is it HTTP or is it HTTPS for BitLearning?
It's HTTP, but because I think I've clicked it and it worked, but because I tried it just before and it worked.
I put it in the chat link for anyone who would like to click on it.
Yes.
I put it as with S.
You can also scan the QR code. It takes you to the same place.
Awesome. Honest, that's awesome. So to give us all the insights on one page and Evernote. That's nice.
Thank you, Stefan, of course. And I will update that note Monday with more stuff. And
that's cool. Pretty cool.
If there are any other questions, anything that, because after we close, I will be sorry. I will think of, I should tell them this or the other thing. I'm sure I will feel that something missing.
To be honest, I think we should have more sessions with you on reinforcement learning. It will definitely
that will be great.
Okay.
Because we can go on specific parts.
Yes.
On this part, yes.
I think it would be a good thing just to have you walk us through or guide us through the different paths we can look at RL.
You can see other families of methods. We can see function approximation, an entrance to deep learning on the deep RL part. Please also, if you would like, all of you today, thank you. You can search for my latest publication with Aris Lazaridis, a survey on deep reinforcement learning, but this is a little bit more advanced. It's a literature review that we did with Aris Lazaridis and on the latest advances on deep RL, but you can Google it and the PDF is available for those more techies in the comment. But we can also think of something like a business workshop, Stefan, that because you see almost 3 years now at Medoi AI, we didn't have the chance to do, some application because it's much more challenging. The cases are not there yet. I mean, that you can really provide something in production with guarantee that we can discuss on many business cases, and we would love to do something on that.
So for everyone who just participated today with reinforcement learning with Anestis, and again, thank you, Anestis, for just being here and telling us all your insights. This was pretty cool, pretty awesome. Just an invitation, as you said. If you have ideas, so I think reinforcement learning will definitely be on the agenda in our future episodes. If you have ideas of what you like to listen to, what you like to hear about the subject, if you have ideas, if you want to maybe code a little bit or check out code for some reasons, let us know. Leave a note either here or send it by email.
Application ideas also.
Yes, application ideas, exactly. I think that's a pretty good suggestion. I put my email in here. Say Swiss. So this one is my email, and you can see it in the chat. You can send it directly to me. I would really appreciate your feedback here, and I will pass it on to Anestis because he brought up the subject. I like that. And thanks again for everyone who joined us today. It will be definitely one of my top videos once we have it up on YouTube, I tell you. And so we will, again, the session was recorded, as you've seen. We will do the post-production now, today, tomorrow, and upload the session to YouTube, to the AI Swiss channel for eternity. And as this for the eternity, right? That's one reward. Let's think about value afterwards, okay?
Yeah, like life, these bottles that stay for like a message for eternity. Okay.
Yes. I think my stomach is full of thousands of questions. I would like to digest it a little bit. I just recognize that's too much. But I'm definitely, I will definitely continue talking with you about the subject.
Thank you.
So thanks again for everyone, and yes, see you next time, and probably Anestis in the future again as speaker here on RL. Thank you and have a nice
evening. See you all. Have a nice evening, all of you. Thanks.